Good morning. So last time we started talking about this idea of work and energy, and we said that work is equal to a force multiplied by a distance. So I'm talking about a particular way that you multiply this force times a distance, and we learned about the dot product. So the dot product of two vectors, or the scalar product of two vectors, A dot B is equal to magnitude A, magnitude B times the cosine of the angle between the two vectors. Now, for us, this will be a force, a distance, and the angle between the two. It's the projection of that force onto the displacement. So work for a particular force, and this would be a constant force, is F dot delta R. That's a dot. So that's a force dotted with the displacement. This is equal to F delta R cosine of theta. Okay? That's how we calculate the work. It has energy of Newton meters or joules or kilogram meters squared per second squared. And I also wrote down something else. I wrote down that the net work done on an object is equal to its change in kinetic energy, where this is equal to KE final minus KE initial. Okay? Kinetic energy is this energy of motion. It's the energy an object possesses when it's in motion. It has a velocity. If an object has a velocity, it has a kinetic energy. Kinetic energy is equal to 1/2 mv squared. So it goes like the square of the velocity. If you have an object of a given mass, has a particular velocity, it has a particular kinetic energy, you double that velocity, you get 4 times the kinetic energy. This is something that was not understood by Newton. Not necessarily that it wasn't understood, it just wasn't studied by Newton. These ideas of energy, conservation of energy, transfer of energy, and so forth really didn't come along until probably the 19th century, Industrial Revolution and other things like that. People got very interested in how energy was transferred, conserved, making things more efficient, and so forth. So I want to show you where this kinetic energy comes from, how we actually can calculate the kinetic energy. Well, first off, I want to show you a little bit of calculus for deriving the kinetic energy, or this work kinetic energy theorem. So the net work on an object is equal to the integral from x initial to x final of the net force acting on an object dotted with dx. Okay? So let me write it like this. This would play the role of our net force as far as being a vector. This is a small little displacement, dx, and you take the dot product of those two. Okay? But since this is one dimension, I'm just going to look at it in 1D. I can get rid of the dot product and these vector signs. It's just F net. That's in the x direction. That's the net force in the x direction multiplied by this little displacement in the x direction. We know that F net is equal to MA. So I'm going to replace this with MA dx because F equals MA. And this would be the acceleration in the x direction. But the acceleration is equal to dv dt. So this is equal to the integral from x initial to x final of m dv dt dx. Okay? We're talking about constant mass problems. I'm going to pull the mass out front. We don't have to talk about constant mass. In this particular simple derivation, I'm looking at constant mass. We can have the mass changing, but that's for another day. So this is equal to the mass times the integral from x initial to x final of dv dt dx. Now, if v is a function of x, okay, then by the chain rule, this is equal to mass times the integral from x initial to x final of dv dx dx dt, and I still have a dx outside. So this looks like a little bit of calculus trickery. For us in physics, this is okay. Mathematicians get nervous about this kind of thing, but we're gonna go ahead with it. Okay. So this is just like you would do with the chain rule. If v is a function of x and you differentiate with respect to t, then you have dv dx, dx dt. And I'm going to move some things around here. This dx can cancel, so we're canceling differentials. That dx can cancel with that one, and we get is equal to the mass times the integral from x initial. Oh, let me see. Yeah, this is okay. No. I'm going to make it a function of v now. And this is v, right? This is dx dt. That's velocity in one dimension, okay, in the x dimension. So this becomes the integral from v initial to v final of v dv. Because the dx canceled, I've got a dx dt here, which is v, and then I have a dv here. So this is equal to the mass. We'll integrate this. This is v squared over 2 from v initial to v final. So I'm just taking the integral of v, and this is equal to the mass times 1/2 v final squared minus 1/2 v initial squared. And that's exactly what I wrote down for delta v. This is equal to 1/2 m v final squared minus 1/2 m v initial squared. Remember, that is the net work done on a system. Okay. One dimension. Works in 3 dimensions, it works in 5 dimensions. Well, okay. We'll just stick to 3. All right. So this is an extremely powerful equation. Very simple, but very powerful, because by knowing something about the work done on a system, we can easily calculate, maybe we know the initial velocity, we know the work done on the system, we can calculate the final velocity, and so forth. So let's look at an example. So I'll just kind of do this example in general. Here we have a car traveling at some velocity v. Okay? Car has mass m. Maybe it's a small car, this kind of cars today, automobiles today, maybe they have about a 1,500 kilogram mass, okay? Something like that, traveling at, say, 40 miles an hour. So this is a 1D problem. So this car is traveling at some velocity v, and you apply the brakes. It takes some distance d for you to stop. So there's a force. I'm just going to draw it as some net force in this direction. I'll call it, F brakes or something. I'll just call it F for this. Okay. So the idea is you're going along, you're traveling at some velocity v, and you apply the brakes, and in some distance you come to a stop. So here's V initial, here's V final, but V final is equal to 0. Okay? So that final velocity is equal to 0. Work kinetic energy says that, I'll write it down again, the net work done is equal to the change in kinetic energy. So in this particular case, the work done is negative Fd, correct? Because the force and the displacement, I'm just calling it little d, we're in one dimension. The force vector and the displacement vector are in the opposite direction. The angle between those two is 180 degrees. The cosine of 180 is -1. Okay? So this force is doing a negative amount of work. Forces that do negative amounts of work slow things down. They decrease the kinetic energy of an object. All right? Forces that do positive amounts of work increase the kinetic energy. So negative Fd is equal to V, let me write it correctly, 1/2 mv final squared minus 1/2 mv initial squared. Okay, but in our case, it's coming to a stop. So V final is equal to 0. So this says that Fd is equal to 1/2 mv initial squared. So if I know the force, then I can calculate the stopping distance. This is what engineers do when they're, engineering brake systems and so forth. Okay, you know the maximum amount of force that's applied, and I'm assuming this is a constant force throughout the motion, then you can easily calculate the stopping distance for a particular velocity. So what would the stopping distance be here? It would simply be D is equal to 1/2 m v initial squared divided by whatever that stopping force is. Yeah. Okay. What happens if we double the velocity? So let's say that you double this initial velocity. How far is it, or how far does it take you to stop? Okay. Previously it was d, but now you double the initial velocity, same force. Get rid of this. It's pretty easy to calculate. Now I have d is equal to 1/2. So I'm doubling the initial velocity, whatever that was. Say the initial velocity was 40 miles an hour. Now I'm doubling it to 80 miles an hour. So 1/2 m 2v initial squared over f. All right. Well, that 2 becomes a 4, and I'm going to write this in a little bit different way. I get a 4 out front times 1/2 m v initial squared divided by f. It takes you 4 times the distance to stop than it did in the first case. If you double your velocity, you don't get twice the stopping distance, you get 4 times the stopping distance. Because you didn't double your kinetic energy went up by 4 times. It goes like the velocity squared. So in this simple example, you had some v initial, it took you d distance to stop, you double that v initial, it takes you 4d to stop. This is why it is so dangerous when you're driving at high speeds that when you follow someone closely at a high speed, that's a lot more dangerous than following someone closely at a lower speed. Takes a lot more distance to stop. All right. So that's one example of the relationship between force and work and kinetic energy. Okay. You can look at, the net forces acting on an object, and calculate the net work. That's typically what you're going to do. You're going to find the net force acting on an object and then the displacement, and from that you take F dot delta R, and that is the amount of work done. That work may be positive, that work may be negative. That work may be 0. Okay. Let's look at a 0 case. Here's a box like we had back in the previous section, sliding along some floor. Here's some applied force, and here's some force due to kinetic friction. Okay? So maybe you're pushing a box along a floor at a constant velocity. Here's some v in this direction, and that velocity is constant. You move the box some distance delta r, all right? So that applied force is pushing it. There is a force due to there's a force due to kinetic friction in the other direction, and it's moving along at a constant velocity. How much work is being done? What is the net work on the object? W net is equal to 1/2 mv initial final squared minus 1/2 mv initial squared. Okay? But V final is equal to V initial, and that's equal to V. It's moving at a constant velocity. That's a very technical way to say it's moving at a constant velocity. All right. So this side is equal to 0. Says that the net work that's being done on the object is 0. That says that F, this is one dimension, F delta R minus Fk delta R, that's the work done by the, this is Fa. That's the work done by the applied force. That's the work done by the friction force. It's in the opposite direction of the displacement. It's negative. So Fa delta R minus Fk delta R, that's the net work, is equal to 0. There's no change in kinetic energy. So the net work is equal to 0. I'll go, let me just erase this. So moving up, this says that Fa delta R is equal to Fk delta R. Fa is equal to Fk. That's what happens in constant velocity problems. You may have forces that are acting in opposite directions, but they're equal. You have an object moving at a constant velocity. Okay? So the applied force must be equal to that kinetic friction force. If it weren't, the object would be accelerating. It would be gaining kinetic energy. If this applied force is greater than the kinetic friction force, that object is speeding up, it's increasing kinetic energy, there is a positive amount of work being done on the object. If this kinetic friction force is greater than, magnitude-wise, than this applied force, okay, the object is slowing down. There's a net negative amount of work being done on the object, and it's slowing down. This is the idea. This is that interplay between work, forces, and kinetic energy. Okay? All right. So now I'd like to talk about potential energy. Potential energy is this energy of position. It's an energy that's based on some system like Earth mass, like you and Earth, or a mass spring system, like you stretch a spring and based on the position of that mass with respect to some other position, okay, there is a potential energy. There's some stored energy in this system. This system has the ability to do work, okay? I think the book makes a pretty big deal about the Earth mass system, okay, for gravitational potential energy. I do recommend that you read the book. I recommend that you read this chapter on potential energy. And there's also a section which we're going to talk about on springs and so forth. But I'm not going to make a big deal about the Earth mass system. I'm going to assume that the acceleration due to gravity is a constant in these problems that at first, we'll look at some other examples, but I'm going to assume that this acceleration due to gravity is a constant in these potential energy problems. So this is gravitational potential energy. It's the energy of your position in the gravitational field. Okay? So let's think about, at first, let's just think about a simple case. Here's a building, and it has a height y. I'll use, this is some height y, okay? I'll use this idea of, that we've used, that this is the y direction for free fall and so forth. Most texts, I think, or many of them use h, and I may slip up and do that as well, but h, y, okay, it's just this distance that you're moving up and down in the gravitational field. So let's say we have an object that starts out here and it ends up here. Yeah, let me start it out. Yeah, it's okay. It ends up here at some position y. All right. We know there's a force on this object based on the fact that it is in the gravitational field. Okay. There's some force due to gravity. This is some 1D system. We're thinking of moving the object just up and down along a line. Okay. So our work energy says that the work done by gravity is equal to the change in kinetic energy. Okay. So let's say there's some external agent that moves this object up very slowly at a constant velocity. Now I'm ignoring this little instant where it accelerates to some velocity and then starts and then stops, okay? Let's just say there's a nice, very, very, very slow motion up to this position y, all right? Well, how much work is done by gravity? Gravity does a negative amount of work on this object. It's moving in this direction, it's moving up, and the gravitational force is down, okay? So the work done by gravity is equal to minus Fg y, okay? That's the work done by gravity. But there was also this external agent that raised the object up to that height, all right? Because it started from rest and it ends at rest. So there's some work done by an external agent in this system. So that external agent must have done some force through a distance, okay? That force, if it's raised at a constant velocity, all right, that force is equal to Fg, and it did a positive amount of work, okay, in this particular example. So there was something that did a positive amount of work, gravity did a negative amount of work, and it got raised up to that height, okay? You see the idea here, I hope? Okay. Back to this. Now we release the object. Okay? Now gravity is doing a positive amount of work and actually increasing the object's kinetic energy. So forget about an external agent. Now there's just something holding it here, and we release it, and the object falls, and right just the instant before it hits the ground, it has some final kinetic energy, okay? So, in that case, the work done by gravity is simply equal to Fg y. Okay? Now, okay, up was positive, but now the displacement is negative and the force is negative in our system, right? The force is in the negative direction, the displacement is in the negative direction, so you get a positive amount of work done by gravity. That gives you some change in kinetic energy. All right? So, this potential energy that we're talking about is what we're going to define as the potential energy of the object is, I'll write it over here. Potential energy is equal to the negative of the work done by gravity. Lots of negatives and positives. That's really bad because that's not little g in this case, it's gravity. But we'll talk about this in a second, okay? So the potential energy, we said that the work done by gravity in raising the object up to here was equal to negative, right? It was equal to something negative. So the potential energy when you're up here is something positive. When the object falls, gravity's doing a positive amount of work, okay? And the potential energy is decreasing. Let's just make it real simple. This is the work done by grav. I should have been writing grav here. Okay, so now I've got you thoroughly confused. However, the potential energy for us is going to be mgy. Okay? It's going to be mgy. It's going to be simply where you are in this gravitational field. And our zero potential energy point can be wherever we choose. Okay? I could choose y equals 0. This would be the easiest place. Y equals 0 here. I could choose y equals 0 here. I could choose y equals 0 right there. Because we're always looking at the change in potential energy. Okay? The change in potential energy. The work done by gravity is the negative of the change in potential energy. Let me show you that. I'm going to leave this up here. So the work done by gravity is equal to delta Ke. So the negative of the change in potential energy is equal to delta Ke. All right. So this says that mg y initial minus mg y final is equal to delta Ke. This says if y initial is greater than y final, y initial is greater than y final, you get a positive change in kinetic energy, right? That makes sense. It's speeding up. That would be a positive amount of work done by gravity. Okay. If y final is greater than y initial, all right, then the object is slowing down. That would be like the object, I'm not talking about an external agent, that would be the object being thrown upward. Gravity's doing a negative amount of work, okay? It's slowing the object down. So y final is greater than y initial. You get a negative amount of work on this side, and that's a negative change in the kinetic energy, which means it's slowing down. Let's look at an example. Okay. Back to the building. Well, we don't even need a building. Okay. Let's say that we're up here at 50 meters. So here's an object that let's give it a reasonable mass, 2 kilograms. Here's a 2 kilogram object. It's at 50 meters height, and it drops, and it ends up down here at 0. Okay, it's in the gravitational field. The acceleration due to gravity is not changing. So I claim that due to work energy, the negative of the change in potential energy is equal to the change in kinetic energy. So I'm going to make this y equals 0. That's the ground, or that's the point at which it passes, y equals 0, and this is y equals 50 meters. All right? So the negative of the change in potential energy is equal to the change in kinetic energy. PE initial minus PE final is equal to KE final minus KE initial. Yeah? What's PE initial? Well, it's starting out up here at y equals 50. So I'm just going to write it out in, well, let's say it's mg y initial. That's PE initial. I'll put the numbers in a second. Y final is equal to 0. So mg y final is equal to PE final, which equals 0. Yeah? What's KE initial? KE initial is equal to 1/2 mv initial squared. That's KE initial. That's equal to 0. I'm starting from rest. Okay? What's KE final? Well, that's what I'm looking for. Equal to KE final. This is going to give us a way to calculate the final kinetic energy, and by knowing the final kinetic energy, we can calculate the final velocity. We're ignoring air resistance. So I'll do that over here. So I have P initial minus P final. P final is 0. So we have mgy initial is equal to KE final minus KE initial. KE final is 1/2 mv final squared. Okay? And KE initial is equal to 0. So I have this. All right? Look. The mass cancels out. Surprise, surprise. Galileo knew this. All right, this final velocity is independent of the mass. I didn't even need the mass. It doesn't matter what the mass is. Okay? So I get V final is equal to 2G Y initial. I'm moving that 2 over here underneath the radical. Okay? All right? So this is equal to 2 times 9.8 meters per second squared times 50 meters, and that is equal to, all underneath the radical. So that's 980. Square root of 980 is about, I don't know, what do you get? 2. .3 meters per second. .3 meters per second. That's the magnitude of V final. Okay. This could be plus or minus, right? All right. So this gives us a neat way to calculate this final velocity without going through the force times the distance or the acceleration and all of that kind of stuff. Okay, this relationship between potential energy and kinetic energy through the work energy theorem. Okay. Now, what if I had defined y equals 0? Let me redraw this a little. I'm going to do the same thing. Now we know it's independent of the mass. So here's y initial. Here's some mass up here at y initial. And I'm just going to call this y final. Okay, it's falling, and it comes to some point y final. All right. I can define the 0 anywhere I please. I'm going to put 0 right here. Okay. That'll be the 0 point. Delta y, okay. Let me rewrite, maybe this will make it a little bit clearer. Negative delta PE is equal to delta KE. That's what we do over and over again. And it doesn't necessarily have to be gravitational potential energy. It can be potential energy of any type, conservative system. So when I say we're going to talk more about that as well. When I say a conservative system, I mean systems where there are no losses, like friction and so forth. Okay, so this is mg y initial minus y final, okay? Because delta PE is mgy initial minus mgy final, so that's equal to delta KE. All right, what is this? This is minus delta y. Okay? Well, look at this. In this case, if I put the 0 point here, y final is something negative, y initial is something positive, and when I take y initial minus y final, I just get delta y. Okay? I just get delta y, right? So I get this distance. This distance is delta y. Okay. Actually, that's good enough. All right. So let's look at an example like that. So here's our building again. Doesn't matter what the mass is. Here's some object. And it's falling. Oh, let me put the bottom of the object here at the top. Okay, it's falling and just before it hits the ground. Okay. I'm going to let this height of the building, just like I had before, is going to be 50 meters. Only this time, the 0 point will be here. Okay, so this is 0.0. So this is 25 meters. This is negative 25 meters. Okay, before we had 0 and 50. mg, y initial, 25 meters. Y final, negative 25 meters. That equals delta K E. Well, what is this? 25 minus a negative 25, you get mg times 50 meters is equal to delta Ke. That's what I'm talking about. You get the same result because you're always just looking at the differences in potential energy. Okay? Where potential energy is mgy, right, in the gravitational field. Okay, for chapter 7, I have already put the homework up. So there are some examples you can look at. I mean, there are some problems you can look at. And also on my YouTube channel, there is some homework help for chapter 7. Now, we haven't gotten to all those problems yet, but you can watch that video as well and look at homework help for chapter 7. Next time, I will talk about work done by non-constant forces like springs. Okay, this is definitely a constant force. We're assuming that the acceleration due to gravity is a constant for this motion, and nothing special about that. Okay, so I'll see you next time.